Last time we talked about sequences, and we considered a sequence to be just a list of real numbers or an infinite list of real numbers. Today we start the topic of series or infinite series, and we consider a series to be the sum of an infinite list of numbers. So instead of just listing them, we're going to be adding them together. There are lots of different kinds of infinite series, but one particular one that's both very applied and very important is called the geometric series, and so we'll pay special attention to that series today. So a quick review of last time. A sequence is some list of numbers. Sometimes we indicate it with just writing out a list of numbers and using the ... notation. Sometimes we give a formula inside the curly brackets and show how it depends on the n. We say that a sequence converges to a real number L if we can make the terms get as close as we like to capital L by taking n large enough. In other words, as we go farther and farther out in the sequence, the terms are getting closer and closer to some real number L. When that happens, we say the sequence converges to capital L. The notation to indicate convergence is often just the limit notation. The limit as n goes to infinity of s sub n equals L. But a shorthand for that we sometimes use is just Sn with a right arrow pointing to L. Our main theoretical result for sequences is called the monotone convergence theorem. And the idea here is that if we know a sequence is both bounded and monotone, either increasing or decreasing, then we know that the sequence converges to something. We may not know what it converges to, and that's okay. We just know that there is some limit. So for series, instead of a list of numbers, we're going to have the sum of an infinite list of numbers. The notation is a capital Greek sigma, so that's here. And the sigma is what stands for sum. Right? So if we see that sigma notation, that means we're not dealing with a sequence, which is just a list. We're dealing with a series, which is the sum of all of the numbers indicated. So the series n equals 1 to infinity of a sub n would be the first term in the series, a sub 1, plus the next, plus a sub 3. We would have a sub 4, and so on. And so that process doesn't end. Now, we are typically not used to adding up infinitely many numbers. We're pretty good at adding up finitely many numbers. So we should expect that this is going to be maybe a little difficult to start making sense of adding up an infinite list of numbers. So just a couple of quick examples of using the notation. The series n equals 1 to infinity of 1 over n. This series actually, because it comes up so often, it has its own name. This is called the harmonic series. And it's the sum of all the reciprocals of the natural numbers. So if n equals 1, I would get 1 over 1. If n equals 2, 1 over 2. N equals 3, 1 over 3. And then the series says, add all of those together. So we would continue to do that out to infinity. Here we have the sum of the reciprocals of the natural numbers squared. So that's going to be 1 over 1 squared, which would just be 1, plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, and so on. Now, a geometric series is one that has a special form. Its form is that the numbers we're adding together all have a common ratio between successive terms. So what that looks like in a general form is something like this. Note that we are, in this case, going to start the sum at 0. That would indicate an exponent x to the 0, which would just give us 1. And so you can think of this first term here as being a, some constant a times x to the 0, but we often just leave that out because it's 1. if the sum has this form, ax to the n, then the first term, ax to the 0, would be a plus ax to the first, which is just ax, plus ax squared plus ax cubed. And to get from one term to the next, notice that we're always just multiplying by x. That's what we call the common ratio of the terms. To figure out whether we're dealing with a geometric series, the way to check is to actually take a look at the ratio of successive terms and just verify that, in fact, they're all the same. So for this particular case, if I took the second term ax over the first term a, the a's would cancel, and I would just get x. Well, if I took the third term, ax squared, and divided by the second term, ax, then the a's would cancel, and the x in the denominator would cancel with one of the x's in the numerator, and I would get x again. If I took the fourth term, ax cubed over ax squared, the a's again cancel. All of the x's in the denominator cancel, leaving just one in the numerator. And so every time I look at the ratio of successive terms, I get x. Right? So we often call x the ratio or the ratio of successive terms. As we'll see later in our study of series, the geometric series is special in a few ways. And one of the ways is that we're actually going to have a formula that allows us to figure out the value of the series. Now that may not sound like such a big deal, but if you think about trying to add up infinitely many numbers, having a formula that tells you what you would get is actually kind of impressive. So we'll kind of have to see as we go on that that's actually a really special case and not something we can generally rely on. There are actually two different versions of the formula. One for what we call a finite geometric series. That's just a geometric series where we stop adding terms after a certain point. And then we have the infinite geometric series where we really are adding up infinitely many terms all at once. So first we take a look at the finite geometric series formula. So this is the formula we can use to simplify calculations if we're adding up maybe a large number of things, but still a finite number of things. Here's what a partial or finite geometric series would look like. We would start with our constant term a, and then we would have terms with our special form, right? They all have successive ratios equal to x, and we would add up finitely many of them, which means at some point we have to stop. So we're going to have a largest exponent on the x. The formula is the following. It works for every value of x except for 1, and every value of a. So on the left-hand side, we have the two different ways of expressing a finite geometric series, either with a shorthand sigma notation or written out. And the news of the formula is that no matter how many terms we have over on the left-hand side, we can figure out the sum of all those terms by taking a times 1 minus x to the n over 1 minus x. So we might have 7 terms on the left, we might have 8, we might have 100,000 terms, we might have 1 trillion terms. But however many terms we have, we can use the right-hand side of the formula to really simplify the work we have to do. The one caution about this formula is to note that whatever the highest exponent is on the x in the sum, let's say we added up terms all the way out to say ax to the 10th. The exponent that we're using in the formula on the right is 1 higher. So in that case, I would be using x to the 11th in the formula. We'll see how that works in an example next up. In our first example, we're using the finite geometric series formula to evaluate a sum. And in many of these, the hard part is recognizing what the a and the x should be. Once we know those, along with the n, we can use the formula. Here we notice that the a is equal to 2. It's the first term in the series. And the x we can find by looking at ratios of successive terms. So if we take the second term over the first, we get 3. If we take the third term over the second, we notice the 2's cancel, all but 1 3 cancels on top, and so we get 3 in each case. We could also just recognize that we're multiplying by 3 every time. The highest power on 3 is our n minus 1. That's equal to 10 in this case, which means that capital N is equal to 11 for use in the finite geometric series formula. So overall, our sum of these 11 terms we can find just by plugging into a formula rather than having to add them all up. So plugging in a equals 2 and x equals 3 and n equals 11, we just have a couple of computations to do to get the end result. So we'll have 2 times 1 minus 3 to the 11th, which is 177,147. And that's all divided by 1 minus 3, which is negative 2. The minus signs on top end up canceling. The 2's cancel, and we end up overall with a sum of 177,146. We could get the same result by adding up all of the 11 terms. For this one, it might be helpful to rewrite the terms to see more clearly what the a and the x should be. We might be able to just recognize that a should be 1, it's the first term, and that means that x will be minus a fourth, because that's how we get from the first to the second term. We would multiply by minus a fourth. If we multiply by minus a fourth again, we would get 1/16 and then minus 1 over 64. So while it might be helpful to rewrite the series to emphasize the role of the minus 1/4, it's not strictly necessary to figure out what the x is going to be. So we can rewrite things as 1 plus minus a fourth plus minus a fourth squared minus a fourth cubed, and so on. The a still is the first term, that's equal to 1. The x is the thing we multiply each term by to get to the next. That's minus a fourth in this case. And the capital N minus 1 is the highest power in our sum. That's 4, so capital N in this case is 5. Once we have our 3 pieces to the formula, a, x, and n, it's just a matter of remembering what the formula is and plugging in the values. So we plug in a is equal to 1, x is equal to minus a fourth, that gets raised to the 5th power, and the denominator is 1 minus negative a fourth, so we do have to be a little cautious keeping track of our minus signs. So overall, our numerator will be 1 minus negative a fourth raised to the 5th. That introduces an extra minus sign which cancels. And then in the denominator, again, we have 2 minus signs, so we'll get 1 plus a fourth. And we can simplify a little bit to get 1,025 over 1,024 in the numerator and 5/4 in the denominator. From here, it's a matter of reducing to lowest terms, and we'll end up 205 over 256, We could get a decimal approximation for that, but it's not necessary. Now, if instead of adding up finitely many terms in a geometric series, we wanted to know the sum of all of the terms, an infinite number of terms, we actually still have a formula we can use, and in some ways it's simpler than the finite formula. So this is called the infinite geometric series formula. Though we haven't really seen that it's the case, it really is kind of a special formula. And it allows us to add up infinitely many terms and still come out with a single value using the formula that we'll present here. So the infinite geometric series formula, or sometimes just called the geometric series formula, is as follows. On the left-hand side, I just have two different ways of expressing an infinite sum, either n equals 0 to infinity of ax to the n, or with the terms written out. Notice that this time there's no largest exponent on the x, right? I've got this plus dot dot dot, which indicates I'm continuing on with an infinite number of terms. Now the result of the formula is that even though I'm adding up infinitely many terms, I know that the value will end up being a over 1 minus x, but it only works if the absolute value of x is less than 1. Otherwise, the series is going to diverge and it won't have a sum. We'll get a little bit of practice in the following examples of using the infinite geometric series formula as well. Our next set of examples ask us to use the infinite geometric series formula to evaluate a sum. The method is much the same as using the finite geometric series formula. The key is to identify the a and the x. There is no capital N in this case because we're adding up infinitely many terms. A is generally the first term in the series, and x is the thing we multiply by to get from one term to the next. So in this case, a is going to be 2, x is going to be a third, and the infinite sum then is equal to a over 1 minus x. In other words, 2 over 1 minus a third. And after some simplifying, that's 2 over 2 thirds, which equals 3. In our next example, we again have an infinite geometric series. A is the first term, that's equal to minus 1. And then x is the thing we multiply by to get from one term to the next. To get from minus 1 to 0.4, we would have to multiply by minus 0.4. We can also just figure that out by dividing successive terms. So I've done 0.4, which is the second term, divided by negative 1, which is the first term. That gives me my minus 0.4. And so the rest is just plugging it in to the right-hand side of our infinite geometric series formula. We would get minus 1 over 1 minus negative 0.4. That's minus 1 over 1.4. And we can get a decimal approximation to that as well. It's about minus 0.7. Sometimes our geometric series will look a little different than we're used to. And this next example shows us that in such cases there are several different ways we can approach evaluating the sum. First, we're going to rewrite the series 5 halves plus 5 fourths plus 5 eighths to emphasize the role of the 1/2. That is the x, which we are multiplying each term by to get to the next term. And then the plus dot 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 indicates that we're in fact trying to add up infinitely many terms in the series. We're used to the first term of the series not having an x in it. So one way to approach this sum is to add a clever form of 0 to it. So I start off by adding 5 at the beginning of the series, which makes it look like our standard a plus ax squared, and so on. And then I just have to remember to subtract that 5 at the end of the series. So all told, the 5 plus the minus 5 hasn't changed the value of the series because they cancel and just give 0. What it has done is perhaps make recognizing that a is 5 and x equals a half a little bit easier. And so the geometric series that starts with a equals 5, we evaluate with a over 1 minus x. So that's 5 over 1 minus a half. And then we have to remember that minus 5 from our trick at the end. After simplifying, we would get 10 minus 5, which is equal to 5. Now we repeat the same example, but we approach it in a different way. We're still trying to make the series look a little bit more standard, and the way we're going to do it this time is to just factor a 5 times 1/2 out of every term in the series. If I do that, I would have 1 from the first term, 5 times a half squared. If I factored out a 5 times a half, would just leave me with a half. 5 times a half cubed would leave me with the 1/2 squared. And inside those parentheses now, we have a normal looking geometric series where a is 1 and x is a half. And that allows me to replace the infinite sum inside the parentheses with the geometric series formula, a over 1 minus x, which in this case is 1 over 1 minus a half. Simplify a little bit, I get 5 halves times 2, which again gives me 5, the result that we got from part A. Finally, our last method is to just agree that we'll take the very first term in our series as a, leaving me with x equals a half still. And then I can apply the geometric series formula, a over 1 minus x, where a is the 5 halves and x is a half. After simplifying, I still get 5 for the final answer. This next example is an example from finance and just shows us one of the many places where the geometric series can be applied. We're making annual deposits of $1,000 into an account. That account earns 3% interest every year. And we're going to make 15 such deposits, so 15 annual deposits. Our job is to figure out the balance immediately following the last deposit. What we're going to do is try to find a pattern that we can take advantage of here. After one deposit, there would be $1,000 in the account. Then a year later, that $1,000 would earn 3% interest, so it would become 1,000 times 1.03, and then in comes our second deposit of 1,000. So right after the second deposit, we have 1,000 times 1.03 plus 1,000. 1 year later, we make our third deposit. Now the first deposit has grown to 1,000 times 1.03 times 1.03, again, the 3% interest it earns in its second year. The second deposit has earned interest for 1 year, so it becomes 1,000 times 1.03. And then finally, we add our third deposit. We could continue keeping track of the formula of the pattern after each deposit, but I think we've seen enough that we can try to write down the pattern after 15 deposits. The very first deposit would have earned interest for 14 years. The second deposit would have earned 13 years worth of interest, so it would become 1,000 times 1.03 to the 13th. Then we would have all the deposits in between up to and including the 15th
deposit. Now, hopefully we recognize that what we have come up with here is a finite geometric series, even though it's written left to right in this case. But the A is equal to 1,000. The X, the ratio of successive terms, 1.03. And capital N minus 1 would be the highest power on X. That would be 14, which means capital N is 15. The finite geometric series formula says that all equals A times 1 minus x to the n, all over 1 minus x. And the rest is just using a calculator to figure out what that sum equals. So after 15 deposits, we would end up with a balance of $18,598.91. So we've made a total of $15,000 worth of deposits and earned about $3,600 of interest. So we'll conclude with at least an outline of the proof for the geometric series formulas. We're actually going to prove the infinite version, and along the way we kind of see the finite version appear. So we'll start by letting S sub capital N be what we call a partial sum of the series. So this is the finite sum, a plus ax plus dot 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 ax to the n minus 1. Now I'm going to do some kind of clever algebra using that sum. And let's take it in steps. So first off, if I multiplied S sub capital N just by x, then I would multiply a by x and get ax. I would multiply ax by x and get ax squared, ax cubed, and finally ax to the capital N. After I do that multiplication, I'm going to subtract x s sub n from s sub n. When I do that, all of the terms will cancel except for 2. I would not have a partner for the ax to the n, so it's not going to cancel, and I would not have a partner for the a. So the result of my subtraction, Sn minus x times Sn, is just a minus ax to the n. All of the middle terms canceled. Once I have that, I can factor out an s sub capital N on the left, giving me Sn times 1 minus x. I pull out the a on the right, giving me a times 1 minus x to the capital N. And then finally, I divide both sides by the 1 minus x. And I can do that as long as x is not equal to 1. What we have just done is demonstrate the finite geometric series formula, which works for all a and all x, except the case when x is equal to 1. Now, if we go a little further, we can develop the infinite geometric series formula, which we do just by taking the limit of our partial sum as we let the number of terms, capital N, go to infinity. All right, so when I do that, I'm taking the limit of S sub capital N. That was a finite sum in the geometric series. So letting n go to infinity means I'm going to be taking an infinite sum now. By the finite geometric series formula, S sub capital N is equal to this quantity. And then the idea is that if I'm taking x to the capital N and letting n go to infinity, that's going to go to 0 as long as x in absolute value is less than 1. So if I took something like a half raised to the n, I would get a half, a fourth, an eighth, a 16th. It would go to 0. If I had something like minus a tenth raised to the n, it would be minus a tenth, 1/100th, minus a 1,000th, 1 over 10,000, so that would also go to 0.
anything bigger than or equal to 1 won't go to 0. So for example, if x was 2, I would get 2, 4, 8, 16, and so on. That would blow up. So it would not converge in that case. But in the case where x to the n does go to 0, right, as we've indicated here, that's enough to finish the infinite geometric series formula, because on the top 1 minus 0 is just 1, and then if I multiply by a, I get the final result. The infinite geometric series is a over 1 minus x, provided that the absolute value of the ratio is less than 1. So that's going to do it for the geometric series section. There are lots of other kinds of series that we're going to run into, and our main job is going to be figuring out when a series converges, in other words, has a finite value like most of our geometric series, and when it diverges. So that's coming up, but for now, we are done.